invariance is also useful for robustness. I wanted to remember the slides we put up. We were talking about Lyapunov functions, right, and robust Lyapunov functions. If you remember this, right, we talked about different types of uncertainty in our simple Lyapunov function case, right, and some forms of uncertainty changed the region of attraction but left the fixed point intact. You remember this? Okay, but other forms of uncertainty, if I just added something, then I don't even the uncertain system might not even have a fixed point, right? And the same thing's true here. If I have an uncertainty about my parameters, there might not be a nominal trajectory, which is valid trajectory of the system for all planes with mass between -1 and 1. I might not have that, right? But invariance is still something you can ask for. You can still say, even if my parameters are uncertain, I can stay inside this funnel. Okay. So you guys, yes, please ask questions.
How do we find rho t? It seems like rho t depends on where is the region of attraction for the time invariant case. So how do we define rho t to get to this one?
Yeah. So if you're asking for stability to the origin, then it is the region of it's some notion of, but it's not a region of attraction because it's finite time. I just try to be careful about but it's some notion of how big of a system can I prove stability to the fixed point in a time. I can prove finite time, properties like stability, right? For invariance, it's actually it's not directly linked to stability. I could have a system that's leaving, that's sort of unstable locally, but I can still find an invariant region that's out here, so that it might be that locally trajectories are going all over the place, but out here I can guarantee they never leave this tube, right? Does that make sense?
But isn't this tube is related to the final region of attraction?
Yes, good. So the one we care about typically is the biggest tube, which dumps into the one So maybe if that's what you're asking, then that's exactly the right answer. Yes. So in this picture, the invariant region that I care about is the biggest invariant region for which the exit dumps into my last funnel, right? So we write that down. It turns out you can write these conditions so if you're working with ellipsoids all the time or whatever, you can write down sort of that condition of one ellipse ending into another ellipse. That's still a semi-definite program. You can write it all down in the language of semi-definite programming and sums of squares. Okay? But that's exactly right. So we want to try to find the biggest invariant set that dumps into that region. Yes?
Do you have some constraint on where it needs to be at the end of your finite time? Like you're looking for it to stay within some areas inside of your trajectory, it needs to sort of leave it right at the last time. And
so this trajectory could have landed anywhere in that circle, is what you're saying, right?
But it needs to get to that circle again.
Exactly. So it has to be right. So the trajectory in general could end anywhere inside this region.
Right.
Ending sort of in the center of the region is a reasonable heuristic because then you might think you get a bigger funnel that comes out. Yeah, and it's going to play out to be numerically nicer for other parts of the algorithm. Yeah, but you're right. That the final condition really has to be somewhere in the interior of this.
What makes it move along the trajectory?
Yeah. How are you guaranteeing that it's going to get from A to B?
Oh, I'm sorry. Okay. All right. So once you have a trajectory and you've stabilized it with time varying LQR, so you have a cost to go function, which is this x transpose st of x. In order to be going downhill on that, so that cost to go function is moving along the trajectory on some schedule defined by time. Right? So if I were to stay in place and the trajectory moves away, you can think about my cost is going to go up if I just stayed in place. Right? So in order to satisfy those conditions, it actually has to be going downhill to keep up with that trajectory. And that's what the feedback controller is going to do, because it's got a feed forward term built into that, right? The u. Yeah, you got that? Yeah.
So you already are assuming that it's going to follow the trajectory, just sort of how far away from the trajectory can you get.
So I wouldn't say I'm assuming. We're verifying that it follows the trajectory. We have a controller that follows the trajectory, and we can ask for what region is it actually following the trajectory. Yeah, that's exactly right. Any other questions? That's good. Oh, sorry.
Yeah, in one of your note slides, you've written that j dot at state 0 is equal to 0. So that's the other one for the time varying case here. So should that be row 0 level set for state 0, and then when the LQR is taking over, it would imply the timing varying case?
So ask the question one more time.
Mike, I want to clarify whether it is j dot 0 t is equal to 0, or should it be the level set
At j equals 0.
Yeah.
So because I wrote it in terms of, so this should be at x naught. It should be relative to the nominal trajectory. So you're right. Let me write at x on the nominal trajectory. Thank you. That's a good catch. Yes. Good catch. Okay. So now we have something more than we had before. We have two funnels, right? And we have a way to take, and get a funnel that was, that went through this area that was not independently stabilizable, but got me back to a region that was stabilizable. Yeah? All right, so here's the next step. By the way, we can compute, so it's a natural question of what systems can you actually compute these for, right? We talked about a little bit about scaling for sums of squares in the time invariant case, and it's a good question about what you can compute them for in the time varying case, and the answer is, relatively complex systems, but not arbitrarily complex systems, right? So the one that Ani had to throw in the slide deck here was a full quadrotor, 3D quadrotor motor with 12 states. Here's a bunch of sort of stable of funnels for the quadrotor model. So 12 state dimensions. We were able to compute these in a little bit of time. Right? How long would you say?
20 minutes.
In 20 minutes for computing along these things, yeah. And I think we could push it a little bit harder, and and every time we get numerically better, the solvers get better, computers get faster, we'll get a little bit better, but it's not going to solve a 100-dimensional system, right? So this is, compared to dynamic programming, which is limited to 4 states or maybe 5 states, let's say, we're in the 12 to 20, let's say, regime for a reasonable thing. And I think that that's important to know. Okay. And the other thing is that you don't have to use LQR. There's nothing central about LQR. LQR happens to be a convenient way to have an initial Lyapunov candidate. Okay. But one of the things that actually Ani has done a lot of nice work on is when you're searching for the funnels, you can actually also, in the sums of squares, search for a better controller, which will increase. If your goal is always to increase the volume of the funnel for which you can prove something, you can change your Lyapunov, coefficients of your Lyapunov functions. You can change rho, but you can also change the control gains. You can't change them at the same time. It's an iteration. In this case, Ani did iterations. Okay, but you can get in practice, if you're willing to go to nonlinear feedback controllers, or even linear feedback controllers that are not LQR, but are somehow designed for the nonlinear system, you can get much bigger verified regions, much bigger funnels, right? So this is the LQR funnel at the top of the Acrobat, and it's sort of relatively small. Okay, you might have some experience with that, I guess. And then doing one with sums of squares control design in the middle, got a much bigger verified basin. Okay, and this is the time varying trajectory swinging up to the top, which is incredibly complicated to look at and looks like it has kinks and weird things in it. But you have to remember this is a projection of a 4-dimensional thing down, so it looks funny. I mean, it might be funny, but it always looks funny because of the projection. Yeah.
So why are you comparing this to dynamic programming? Because dynamic programming tells you what to do in every single state, whereas this one it tells you what to do within that funnel, only within that funnel.
That's true.
So
is it a fair comparison?
It's a fair comparison.
You're asking me if that's a fair comparison, right? So. I think it's. I'll try to justify it being a fair comparison in a few slides. Yeah.
Okay.
But it's not going to. So I haven't actually said anything about optimality in there. So it's already, we're doing less than dynamic programming even inside the funnel. We're just proving that it's going to work. But the dynamic programming on a discretization, it's hard to say anything about the continuous system. So they're really good at different things. But I'm just saying, sort of on the scale of what size problems can you address with these, they're slightly different places. Okay.